this video, you'll see how voltages appear throughout a basic Whirlpool-made gas dryer for different operating and failure modes. This schematic walkthrough will help new technicians understand in detail how such gas dryers' electrical topology works and introduces experienced technicians to how using point-to-point voltage difference diagnostics can both speed up and more definitively help them reach a diagnostic conclusion. Here we have a basic Whirlpool gas dryer schematic. So as you plug the dryer in and you have the door open, your neutral appears over here, passes through the door switch, and shows up at the right side of the drum lamp. I'm going to use blue for neutral and black for L1, which is 120 volts with respect to neutral. L1 shows up on the left side of the drum lamp and appears over here at these parts of the timer and the left side of the timer motor. Since you have a neutral over here and L1 right here, the voltage difference is 120 volts and the drum lamp illuminates. When you close the door, neutral is diverted from the drum lamp to the right side of the start switch and the centrifugal switch, as well as this part of the timer here, where it's ready and waiting to be connected to the right side of the timer motor. The drum lamp goes out, of course. When we advance the timer to time dry, these contacts are going to close here. This contact's going to close here. This brings L1 through the motor to the left side of the start switch. Since there's no current flowing, the impedance of the motor has no effect on L1 and it passes cleanly through. There's no voltage difference across it. You're going to get 120 volts across the start switch, across the centrifugal switch. And now that this timer contact is closed, we're going to have 120 volts across the timer motor. The gas ignition circuit has 120 volts throughout the entire circuit with respect to neutral, but no voltage differences, so no current flow is flowing and no activity is occurring in that part of the circuit. Now, when you press the start switch, neutral appears on this side of the motor, whereas we still have L1 over here, and both the main and start winding are energized. You have 120 volts across these windings. The start winding is physically and electrically out of phase with the main winding, which causes rotation. At the same time, the igniter starts glowing because we now have 120 volts difference across it. We still have L1 all the way up to this point right here because the flame sensor is closed. We have essentially 0 ohms here. And the main winding is shunted. It's not in the circuit at this time. Both the hold and assist coils have 120 volts across them, and the safety portion of the gas valve opens. At this point, we have released the start switch because the motor has reached its target RPM, and the centrifugal switch has flipped over here. Now we have 0 volts across this, and we have neutral along this entire portion of the circuit, along the right side of the motor and on the left side here of the gas ignition circuit. Now that this centrifugal switch has flipped over here, the motor is now self-sustaining. We don't need to have neutral supplied to the motor anymore via the start switch since the centrifugal switch has taken its place. The flame sensor is still closed because it has not yet detected enough radiant heat from the igniter to open. And that's what's going to happen next. Now, once the flame sensor opens, you're going to have current flowing through the igniter. The igniter will start to cool down, and the main winding now has greater than 110 volts across it, just about 120, but not quite because there's still a small voltage drop across that igniter. But the hold coil still has 120 volts across it, and since there's a small voltage drop across the igniter, the assist coil no longer has full voltage. It has the same voltage as the igniter does, which I've measured usually to be somewhere around between 3 and 5 volts. We don't need the assist coil anymore because it's already done its job. The hold coil is now holding the safety portion of the gas ignition system open. That safety plunger is open, and the main coil is now energized, and that portion is open, and gas is now flowing and is lit because the igniter was glowing white hot, and now the flame is keeping the flame sensor open. And this is the target state of the gas ignition circuit right here. As long as these states persist, the gas will continue flowing and will continue to be ignited. Now, when the operating thermostat, when the gas dryer reaches its target temperature, the operating thermostat will open. and you'll have 120 volts from the left to the right side of it. If you had a voltage pen, it would give you a signal here and no signal there, and that would tell you that the operating thermostat is open. And neutral appears throughout the entire gas ignition circuit. There are no voltage differences here, thus there is no current flowing through this circuit. It is completely dead at this point. This slide illustrates what happens when the timer is set to auto dry. When the timer is set to auto dry, the motor does not turn as long as the operating thermostat is closed and the gas ignition circuit is activated and ignited gas is flowing. It'll stay this way until the operating thermostat, the dryer reaches temperature and the operating thermostat opens. When this happens, neutral appears at this point right here because there is no current flowing through the circuit, and neutral makes its way all the way through the gas ignition circuit and shows up on this side of the timer motor. It is at this point that the timer motor starts to turn, only when the flame is out. As the dryer cools down and the operating thermostat closes again, then the timer motor will stop and the gas ignition circuit ignites, and until the temperature again reaches its target temperature, the timer motor will have 0 volts across it. And then once that target temperature is reached, you then have neutral passing through the entirety of the gas ignition circuit and appearing on the right side of the timer motor, and it will proceed until the timer reaches the end of the cycle. This slide illustrates airflow. It is simply a state where these set of timer contacts are open and L1 is not allowed to make its way through the gas ignition circuit and cause current to flow through it. As such, neutral will make its way all the way through the gas ignition circuit, make its way through all of the thermostats. It'll show up at this point right here, and you'll read 120 volts across here. And so if you had a voltage pen, you would get a reading right here, and you would not get a reading right there, indicating a voltage difference of 120 volts across these two contacts here. This part of the video illustrates some of the failures that occur in Whirlpool-made gas dryers and the associated voltage states that you would see. Using a voltage pen, you would be able to detect such voltage states and be able to determine from these voltage states which components are likely bad. In fact, you can do the vast majority of troubleshooting on a gas dryer using a voltage pen. In this slide, we have time dry, no heat, and a failed centrifugal switch. If the centrifugal switch has failed, you would press the start button. The motor would start to wind up, but as soon as you release the start button, it would just wind right back down because centrifugal switch would never have flipped over to the right and allowed neutral to be sustained on this side of the motor. As well, neutral would only make it to the gas ignition circuit when you press the start button, and you would hear the valves click, but as soon as you release the start button, the circuit would lose neutral and ultimately would not ignite. This failure, time dry, no heat, based on failed timer contacts, is based on the fact that these contacts right here are open in the timer, even though you have advanced to time dry. In this case, you would measure 120 volts across these contacts. So in this case, if you were to have a voltage pen, you got 0 volts here and 120 volts here, or a reading from the voltage pen, that would tell you had 120 volts across contacts that should be closed. So neutral would appear over here because it has made its way through this part of the circuit here, through the gas ignition circuit, through all the thermostats up to this point right here. This slide, time dry, no heat, or open thermal fuse, would be very similar to the previous slide where you had a break in the circuit over here, but instead we have a break in the circuit over here. And you're going to get 120 volts across that thermal fuse. This, by the way, is one of the most common Whirlpool-made gas dryer types of failures where the thermal fuse has opened up and it's just simply disallowing L1 from getting to the gas ignition circuit. So neutral would make its way all the way through the gas ignition circuit and appear right here, and L1 would be stuck right here. So you had a voltage pen, you would measure 120 volts here, and you'd get no reading over here, which would tell you that the thermal fuse is open. You could do that even without even pulling the thermal fuse out or disconnecting any wires from it. So that's the beauty of using voltage pen troubleshooting. In this failure mode here, we have an open thermal cutoff, which means that you have 120 volts across that thermal cutoff. And this is very similar to the previous slides where you just had a break in the circuit that was disallowing L1 from making it to this portion of the circuit over here. So you've got neutral that's making its way all the way through the gas ignition circuit, showing up on the right side of the thermal cutoff on the schematic, and you have L1 over here. So you would with your voltage pen, you would pick up 120 volts here or get a reading there, and no reading there telling us you have a voltage difference of 120 volts across that thermal cutoff. In this failure mode here, where the radiant sensor is stuck in the open position, the main gas valve is going to get approximately 120 volts across it, a little less than that. It's greater than 110 volts. Again, because you're going to have a slight voltage drop right across there. But the gas valve will be energized, the hold valve will be energized, but the assist valve never will have gotten any voltage to speak of, so it did not open this portion of the gas valve. And that's very fortunate, and that's why they have this arrangement here. This is one of the cases in which the assist valve comes in and saves the day, because if this flame sensor was stuck in the open position, this assist valve never would have allowed this part of the gas valve to open, and you're not going to get any gas flow. Otherwise, you would get gas flow without the igniter being lit, and that would be disastrous. In this case, your voltage pen would register over here. You get 120 volts here. And over here, you're not going to get anything from the voltage pen because you're just going to have a couple of volts right there. And that would tell you that you have almost 120 volts across the radiant sensor, which would tell you that that radiant sensor is open and bad. In this case, you have an open igniter, whereas you're going to have neutral over here, and you're going to get L1 is going to pass all the way through here. You're not going to have any current flow over here. You're going to have some current flow from here to here because your hold valve is open. Your hold valve is energized. Also, your assist valve is energized. But your main valve is not energized because you have 120 volts on this side, 120 volts on this side, which your voltage pin would tell you. But you have a voltage difference of 0 volts, because 120 minus 120 is 0. You have 0 volts across the main valve, so the main valve not open. So the first portion of your gas valve does open, the second portion does not. And so if you have an open igniter, in this case, gas will not flow. If you have, in this case, a failed main gas coil, your igniter will glow and your flame sensor will open, and it will result in 120 volts across the main coil. But since there's no continuity there, it's not going to energize, and it's not going to pull that plunger up. But the assist and hold coils will do their job, and that first portion of the gas valve will open, but the second portion will not, because the main gas valve coil is open. In this case, you're going to read 120 volts on this side and approximately 0 on this side. And what's going to happen in this case is it's just going to keep trying to light the flame. The igniter is going to go out, it's going to come back on, and it's going to glow, and the flame sensor is going to open. And once the flame sensor opens, the igniter loses voltage. It's going to go out, and since there's no gas, ignited gas, then this is going to keep this is going to keep closing, and you're just going to get this cyclical opening and closing every, say, 5 to 10 seconds. You're going to hear this thing continue to try to activate the main valve. And so if you hear that, then you likely have a main coil that is open. So that's it. Those are some of the voltage states that you would see in a Whirlpool made gas dryer in both operating and failure modes. And how would you be able to use a voltage pen in order to detect those modes and to be able to give you a really good idea as to how the voltages are mapped out within the circuit without having to remove any components, and more accurately and get you more quickly towards your final diagnosis. Thanks for watching. I hope you found this video helpful and informative. If so, please give it a thumbs up and subscribe to this channel.